economic order quantity model or EOQ model. It is a deterministic model. We assume that the demand and lead times are deterministic, there is no uncertainty, and we want to find the order quantity and the order point that will minimize total costs. And we assume that the item purchase cost is fixed. We have inventory holding cost and we have fixed ordering cost. Let's see one example with two different plans and see how we will approach this specific model. For this model, for this example, we will assume that the lead time is equal to 0 and we will not allow for any back orders, so we will satisfy all of the demands with on-hand inventory immediately. Assume that we have a yearly demand equal to 1600, and then we have two plans for satisfying this demand. In plan A, we will make orders of size 400. If we have orders of size 400, then we need 4 orders. 4 times 400 equal to 1600 to satisfy this demand. So we will pay this the ordering cost, fixed ordering cost 4 times per year. In plan A, the average inventory level is equal to 200. So we will pay on average for holding this much inventory. In the plan B, we will make orders of size 100. If we make orders of size 100, then we need to make 16 orders to satisfy this yearly demand. 16 times 100 will give us 1600, which is equal to the yearly demand. As you can see, we will make more orders, so we will make more, we will pay the ordering cost, fixed ordering cost more often. So let's say we can say in total the ordering cost that we are paying in plan B is greater than the ordering cost in plan A. On the other hand, average inventory level in plan B is equal to 50, and we are keeping on average less inventory, so our inventory holding cost compared to plan A is less. To summarize, in plan B we have a higher inventory ordering cost, fixed ordering cost, but we have a lower inventory holding cost. And what we want to find in our problem is a queue that strikes the best balance between inventory holding cost and fixed ordering cost. We will use this notation. We will use D as the total demand per year or per unit of time. It depends on how we define the unit of time we are working with. Then we have S, which is the cost to place a single order, or it is the fixed ordering cost. And then we have H, which is the cost to hold 1 unit of inventory per unit of time. And then Q is the order quantity, and here it is our decision variable. We can write total cost of inventory as a function of Q. So the total cost will equal to the annual holding cost plus the ordering cost. For the holding cost, we just need to multiply H, which is the inventory holding cost per unit of time, by the average inventory, which is Q over 2. And the annual ordering cost is the number of orders that we make per year. So if we have a demand equal to 1600, and if we make orders of size 400, then 1600 divided by 400 will give us 4, which is the number of orders that we make per unit of time or per year, as we can see here. So S will be multiplied by the number of orders that we make each year. So this will give us the total cost. We can plot these different cost terms as a function of Q. As you can see, this red line is the inventory holding cost, and then we have this blue curve, which is the ordering cost. And the summation of this cost, which will give us this gray curve, which is the total cost. To find the cost, minimizing order quantity, we will take the first derivative of the cost function, total cost function with respect to Q, and then solve it for Q. Put it equal to 0 and solve it for Q, so it will give us a Q equal to the square root of 2 times D times S over H, which is called economic order quantity, or EOQ. The optimal Q, which will minimize over total costs, denoted by Q star, is in fact the point that this total cost curve will reach its minimum. And as we can see here in this figure, this point is exactly the point at which the two cost terms for inventory holding cost and ordering cost will cross each other. In other words, at optimality for an EOQ model, the inventory holding cost and the ordering cost will be equal to each other. And then the next question would be when to make an order. If the lead time is equal to 0, so we will make an order whenever we reach our inventory level reaches 0, so we will immediately receive the order. Otherwise, if we have a lead time equal to L, which is deterministic, of course, because we assume that it is a deterministic model, then the reordering point simply is the average demand, or let's say the total demand, because here we do not have any uncertainty, so average demand would be equal to the total demand. So it is the average demand or total demand during the lead time. And the lead time, of course, is the time between placement of an order and its receipt. So reorder point is the demand per unit of time multiplied by L, which is the lead time. And what we need to be careful here is that this time unit for the demand should be consistent with the time unit that we are using for our lead time. So if the lead time is expressed in weeks, so the demand should be also in weeks. If it is in years, so demand should be also in years. Let's see a small example here. We have a demand equal to 4,000 per year. Fixed ordering cost S is equal to 50 per order, and then we have H, which is inventory holding cost, which is equal to 15 per unit of time per unit of product. So the EOQ, which is to calculate the EOQ, we just need to use the formula. So it is the square root of 2 times D, which is 4,000, times S, which is 50, divided by 15, which is H. That will give us 163. And then if we substitute this Q into the total cost function, we will get the total cost equal to 2,450 for at minimum, at optimality.